Everybody, and I would like first of all to thank the organizers for inviting me to present a talk about high-redshift quasars, and in particular I would like to focus on how to feed gas to them and therefore also on their environment. As a matter of motivation and introduction, as we have seen many times, I'm sure, and in this conference and today, quasars at high redshift already host very massive, supermassive black holes in their centers. And at the same time, they're hosted by very massive and very star-forming galaxies, as shown by recent submillimeter observations. In this context, one of the main puzzles, I think, is actually how to feed the gas that is needed to both feed the fastly accreting supermassive black hole and the highly star-forming host galaxy. From a theoretical perspective, many theoretical studies and simulation studies find that these quasars, to predict these quasars to be found at the high density peaks of the dark matter distribution at that time, and to be surrounded by overdensities of galaxies. Therefore, quasars at high redshift can also be used as signposts for the first overdensities. But from an observational point of view, I would like to point out a question mark here. So what are we actually seeing in observations? Before moving to the very high redshift universe, I would like to make a small detour to what we see at intermediate redshift. So from redshift 1, let's say, to redshift 4. In this case, there has been studies of large samples of quasars where we have seen that the correlation functions of these quasars show that this object, especially at redshift greater than 2.5, are hosted by very massive dark matter halos, and therefore there is a strong quasar clustering. But what is happening at even higher redshift? Again, since this is a very much focused conference on supermassive black holes, I would like to spend one slide to talk about one of the challenges, I think, of studying the environment of quasars at high redshift, which is actually to select galaxies which we think are physically related to the quasars. I'm sure you all are very familiar with it, but I find it useful to take a step back and summarize this. So first of all, one way is to search for Lyman-Break galaxies. So these objects are usually detected in the rest frame UV, and through their breaking their spectrum due to the intervening IgM absorption. These objects are selected with deep imaging and with broadband filters. The positive side of this is that this is quite a cheap selection because you can imagine several quasars fields in several fields in a relatively short amount of time at large telescopes. On the other hand, the negative side is that these sources are selected within a large redshift range. Therefore, they have large redshift uncertainties, which might dilute any overdensity signal. Another way of selecting galaxies is by considering line emitters. So for instance, Lyman alpha emitters. In this case, you have both a break in the spectrum and a strong emission of the Lyman alpha line that you can detect with deep narrowband imaging, together with indeed broadband observations. The positive side in this case is that there is a small redshift uncertainties, a delta Z of 0.1, let's say. On the negative side, too, you need to have a very precise redshift determination of the quasar itself to make sure that the redshift is falling in within the narrowband filter response. So you're not probing a physical region which is actually not around the quasar. On the other hand, it is also thought that these sources are less clustered with respect to Lyman-Break galaxies. Finally, another way of selecting galaxies, which is not focused on the rest frame UV emission, is by selecting submillimeter galaxies. In this case, you study the emission of the dust and the cool gas in the interstellar medium of these galaxies, and one can do this indeed with submillimeter observations. The positive side of this is that if you use instruments such as, well, facilities such as ALMA, you have a very accurate membership determination with the line emission of these galaxies. On the other hand, you only select dusty sources, and you select sources over a small field of view around the quasar. So again, what is the situation at redshift 4? In this case, there has been studies indeed focused on galaxies and quasars cross-correlation functions around quite a large samples of quasars. In this case, for instance, I show you here the correlation function of LBG and Lam-and-a-half emitters and quasars, as reported in the nice papers from Garcia Vergara, 2017 and 2019. And they found that there is a strong clustering of these two types of galaxies around quasars, at least at this redshift. So, but then what happens when we approach the epoch of reionization? In this case, things get a bit more complicated and unclear, I would say. Indeed, at even higher redshift, there has been so far several studies, but mainly focused on a single fields. In order to represent them in a more graphic way, I show you here the field of view that the studies have considered and the redshift. So I represent here basically a collection of literature studies that has tried to find Lyman break galaxies or Lyman-half emitters around quasars at high redshift, with other overdensity, meaning a case in which a quasar was found in an overdensity, more or less serendipitously. And I also show the typical sizes of instruments that have been used in order to study this environment. Also, this is the region of the protocluster area. So what we think from simulation is supposed to be the area covered by a protocluster around the quasar itself. So in this case, you see that there is a mixture of results. There has been 18 quasars field studied so far at redshift greater than or roughly 5 for LBGs and Lyman-half emitters. And 9 has been found overdense, while 5 have found with no overdensity. I'm just citing one example. I think one that has been particularly studied was J1030 that has been studied with a plethora of instruments, first in imaging with HST and then by Morselli with the LBT, and later on several follow-up observations with sublimeter and optical few such as MUSE have confirmed the presence of an overdensity around the source. On the other hand, as you may see, 9 plus 5 is not equal to 18, so because we have some fields that have actually uncertain results. So some of the fields that are even studied by different groups with different techniques on different results. I cite here a few examples. One is J0305, for instance, where Otta in 2018 could not find an overdensity of Lyman-half emitters with the Subaru telescope. But on the other hand, in our study led by Emanuele Farina with MUSE, we have found the Lyman-half emitter very close to the quasar itself, as you see here in the plot, which might suggest the presence of a strong overdense environment in this around this quasar. On the other hand, another example can be J2329, where an overdensity has been found by Utsumi back in 2010. But Lyman-half emitters were not found around this source by Goto in 2017, and even an underdensity was found. As sort of a bonus, Drake in 2019 could even find a very bright Lyman-alpha halo around this quasar, which means a very strong and active gas feeding around the source. So I find all of this collection very puzzling. So I just list here a few of brainstorming ideas of why we're seeing this. One of the reasons could be that indeed we're only expecting few sources, so we are subject to cosmic variance. Another very important, I think, is that we have indeed a variety of overdensity measurements and a variety of galaxies selected that might dilute any sample results, let's say. Another point might also be that the field of view is too small to actually cover the entire protocluster extent. Indeed, the quasar itself is emitting ionizing radiation, which is heating the gas around the quasar, preventing the gas to cool, form stars, and eventually form galaxies. In this case, we might not be able to see galaxies around the quasar if we only inspect a very small area around it. These have been maybe observed before. For instance, as I showed you before, Utsumi could find Lyman-break galaxies, but not in the few megaparsec close to the quasar, which are thought to be the region ionized by it. Very similar result Adams at a slightly lower redshift case. On the other hand, very recently, there has been also other studies finding massive companion galaxies very close to the quasars themselves. And for instance, Sarah Bosman in 2019 has very nicely argued that the star formation suppression is happening in lower mass halos, which means that we still should be able to see galaxies in the vicinity of the quasars. One other reason that I would like to spend a few words more in is that these galaxies might be more dust obscured than observable in the rest frame UV. And this is something that has been explored particularly in the last years. As shown by Eduardo before, there has been a boost in the studies of quasars and quasars environments through facilities such as ALMA, but also NOIMA, in the sense that the original aim was indeed to study the dust and the cool gas emission from the host galaxy of the quasar. And what we did not expect to find was that these sources are often, in a quarter of the cases actually, a companion, let's say, from submillimeter galaxies in their vicinities, which are both close in the physical and the spectroscopic space, let's say. So these sources are really interacting with the quasar itself. If, for instance, you plot the cumulative number of the companions in the field as a function of the projected distance to the quasar and compare it with what is expected in case of no quasar, so the dashed lines here in the case of two different background, you see that these are indeed highly overdense regions in the early universe. In order to understand these cases and the properties of these galaxies, what we did was back in 2019 was having a multi-wavelength characterization of these companion galaxies and follow-up with deep imaging with HST and with the Spitzer facilities. The bottom line here is that we basically did not observe any emission at a significant signal to noise in a few of the companions that we previously selected with ALMA. And we also compared the limits on the spectral energy distribution of these sources with SEDs observed for close by nearby galaxies, let's say. And we basically saw that these objects are very similar to ARP220, so powerful OLIRCs galaxies, but up to redshift 6 indeed. We can also see how much of the star formation is actually happening in the obscured versus unobscured phase. And what I plot here is the fraction of the obscure star formation rate as a function of the stellar mass or limit on the stellar mass. And for the companions that we investigated around quasars, but also for SMGs or LBGs at high redshift or quasars, or sorry, galaxies at lower redshift. And what we saw basically is that the star formation is very highly dominated by the obscured fraction. So indeed, these objects, as we may have suspected, are powerful SMGs. Finally, we can also place them in the context of the star formation rate versus stellar mass plot. So the main sequence of star-forming galaxies at redshift 6, if you believe this thing exists as redshift 6. So this we can compare this with observations and with models and see that at least with the limits that we have so far, all of these companions are actually falling in within the main sequence at the redshift. We hope that with future facilities such as JWST, we will be able to actually see the stellar component from these very obscured companion galaxies. That would indeed would be very extremely interesting. So let me just get back to my shopping list here, and I would like to also, I guess, end my talk a bit talking about other very interesting sources. And this point is not really about answering the question of why so many different results, but also about maybe finding a sample of high redshift quasars, which are actually found in overdense environments. So I'm talking about quasars showing very strong radio emission, radio loud quasars. Indeed, this type of sources, radio bright sources, both radio loud quasars but also radio galaxies, have been univocally found in overdense environments over a large redshift range. So from the local universe up to the epoch of reionization, basically. I show you here, for instance, a couple of examples from a spectroscopic follow-up of galaxies. Lamar emitters found around radio galaxy at redshift 5 with force. That was for a long time the highest redshift radio galaxy discovered. But also there has been a strong signal of overdensity of LBGs in the radio loud quasars redshift 6, both firstly found with HST and afterwards also confirmed with MUSE at the VLT. And basically these two studies have been the only ones focused on bright radio sources in the epoch of reionization. But this might actually be the type of sources to focus on if we are interested to find overdense environments. What we have obtained recently, and I find very interesting, is that we have focused our attention on another quasar, radio loud quasar at redshift 5.7. We previously known very precisely the redshift of this quasar from CO observation, and we confirm it with recent ALMA observation that found a very bright continuum emission and also very bright C+ emission. And this redshift places the objects very precisely within the response of a narrowband filter available at the first two camera at the VLT, with environment with deep imaging both in the narrowband and in the broadband. And we found several Lyman alpha emitter candidates, which might be a really good sign in case of an overdensity found around this source. So for instance, if we again plot the number of objects, the cumulative number of objects as a function of distance from the source, and compare it with the case of no clustering, we see that we might indeed be observing a potential enhancement of LEEs in this field. So it would be very interesting to obtain follow-up observations in order to spectroscopically confirm some of these and study some of these sources. Finally, I would like to with a few words on the radio loud quasar that Eduardo talked about in the last part of his talk. Indeed, we have recently found the quasar, which is currently the highest redshift radio loud quasar known at redshift 6.8. And I show you here the rest frame UV spectrum of the quasar, which shows, I think, beautiful emission lines that are also very interesting in the case of studying the inner properties of the quasar itself, such as carbon 4 outflows or the black hole masses. But I would like to focus on something else, so on the environment again. In this talk. Indeed, this source was firstly observed with FIRST in the 1999 and was detected as a bright radio source. And this is also how we found this quasar. On the other hand, we also obtained recently VLA follow-up observations of this source. And I think we find very puzzling discoveries, I think. On one hand, we see that the quasar itself has a flux which is half of what it was recovered 20 years ago with FIRST. So we might be seeing hints of radio variability of this source in the span of 20 years. And so we are currently following this up with higher resolution VLBA observations. And as well, we would like to continue monitoring this source to see if we have any further evidence of variability. On the other hand, as you also see in the postage stamps from the VLA, we also found another source very close to the quasar at a distance of 20 arcseconds, which was not detected in the first images and is actually even brighter in radio than the quasar itself. So this might be another variable source and potentially a companion source at the redshift of the quasar, which might signal again an overdense environment. We were lucky because this quasar is also found with a very precise redshift that coincides with the narrowband filter response, this time on board of HST. So we asked and obtained observation with narrowband broadband with HST, and observations are scheduled hopefully to start soon in order to study for the presence of LEEs and LBGs in this environment. So again, these are my conclusion. I think the environment of high redshift quasar is a very interesting and still very open puzzle, and we still have very different directions in which we can tackle it. such as, for example, having a much more larger sample of quasars studies in a more consistent way, or focusing on fields but obtaining multi-wavelength and multi-scale characterization. And in case that we are really after over-dense environments and to study any connection with properties of the quasars themselves, we have a collection now of radio bright sources in the epoch of reionization that would be very interesting to explore. So I would like then to thank you for your attention.